Tonight, we're embarking on a celestial journey to explore one of the most captivating phenomena in our universe: the secret lives of planetary satellites, those dancing companions we call moons. Before we drift into the starlit realm of these celestial wanderers, I'd love to know where in the world you're listening from tonight, and what time it is in your corner of the universe. There's something wonderfully poetic about the fact that no matter where you are, you might be able to step outside and see our own moon, that same gentle face that has watched over humanity for millennia. If you find tonight's voyage through the cosmos soothing, I'd be ever so grateful if you gave this video a gentle like, perhaps subscribed, or even left a comment sharing your favorite moon or planetary satellite. It helps this little corner of cosmic calm reach other stargazers who might need a peaceful pause in their evening. Now, I do hope this isn't so fascinating that it keeps you awake, but if it does, well, at least you'll drift off knowing a bit more about the beautiful dance happening right above your head. So settle in, let your shoulders drop, take a slow breath, and let's begin our gentle exploration of these mysterious worlds that waltz through space in an eternal cosmic ballet. When we look up at the night sky, we often focus on the stars, those distant suns twinkling like scattered diamonds against the velvet darkness. But there's another story unfolding much closer to home, a tale of gravitational partnerships that have shaped not just our own world, but countless others throughout the solar system and beyond. Our moon, that familiar silvery companion, is just one member of an extraordinary family. Throughout our solar system, there are over 200 known moons, each with its own personality, its own secrets, and its own remarkable story. Some are larger than planets, others no bigger than city blocks. Some harbor hidden oceans beneath icy shells, while others are covered in active volcanoes that paint the cosmos with their fiery displays. These aren't just rocks floating aimlessly through space. They're dynamic worlds, each locked in an intricate dance with their parent planets, influencing everything from tides and weather patterns to the very stability of planetary rotation. They're time capsules, preserving the history of our solar system's formation. They're potential harbors for life, hidden laboratories where the building blocks of biology might be quietly assembling in the darkness. Consider Europa, Jupiter's ice-covered moon, where beneath a frozen surface lies an ocean that may contain more water than all of Earth's oceans combined. Or Titan, Saturn's largest satellite, where methane rains fall on hydrocarbon lakes under a thick orange atmosphere. There's Io, a world so volcanically active that it essentially turns itself inside out every million years, and Enceladus, a small moon that shoots geysers of water hundreds of miles into space from cracks in its south polar region. Each of these worlds represents a different chapter in the story of how moons form, evolve, and interact with their cosmic neighborhoods. Some were born from the same disk of material that formed their parent planet. Others are captured asteroids, cosmic wanderers that found themselves ensnared by gravitational embrace. Still others, like our own moon, may have formed from the debris of colossal collisions that reshaped entire worlds. But perhaps the most beautiful aspect of these celestial relationships is the dance itself. Moons don't simply orbit their planets in perfect circles. They waltz in ellipses, they tug on each other with invisible threads of gravity. They raise tides not just in oceans, but in solid rock, stretching and flexing their parent worlds like cosmic stress balls. This gravitational choreography creates resonances, mathematical harmonies where moons influence each other's orbits in predictable patterns. 3 of Jupiter's largest moons, Io, Europa, and Ganymede are locked in what scientists call a lapless resonance, where for every orbit Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. It's as if they're dancing to the same cosmic rhythm, their movements synchronized across the vast emptiness of space. These orbital relationships aren't just mathematically elegant, they're practically important. The gravitational flexing that results from these dances generates heat through tidal friction. And this heat is what keeps subsurface oceans liquid on moons that should be frozen solid at such distances from the sun. In other words, the dance itself creates the conditions that might make life possible. As we continue our journey tonight, we'll explore how these moons formed in the chaotic early days of our solar system, how they've evolved over billions of years, and how they continue to surprise us with their complexity and beauty. We'll visit the volcanic forges of Io, dive beneath the ice of Europa, float through the methane atmosphere of Titan, and peer into the geysers of Enceladus. We'll discover how studying these distant worlds helps us understand not just our own moon, but the potential for life throughout the universe. Because in the gentle gravitational embrace between planets and their satellites, in the tidal heating and orbital resonances, in the hidden oceans and exotic atmospheres, we find some of the most promising places to search for life beyond Earth. So as you settle deeper into your evening, let your mind wander to these distant shores, these alien landscapes, where the physics of orbital mechanics creates wonders that rival any earthly paradise. Let the rhythm of gravitational forces lull you toward rest, knowing that right now, as you listen to these words, countless moons are continuing their eternal dance through the cosmos, writing stories in motion that began billions of years ago and will continue long after we're gone. Tonight, we begin with the most familiar of all satellites, our own moon, that constant companion whose gentle light has guided lovers and poets, tides and travelers throughout human history. Our story begins not with telescopes or computers, but with something far more fundamental: gravity. In the moments following the Big Bang, when the universe was nothing more than a hot, dense soup of particles expanding into the void, gravity was already at work. It was patient, persistent, and quietly revolutionary. Picture the early universe as a vast ocean, nearly perfectly smooth, but not quite. There were ripples, tiny variations in density that would have been invisible to any observer. These weren't dramatic mountains and valleys, just the faintest whispers of difference, 1 part in 100,000. But gravity noticed. Gravity always notices. As the universe expanded and cooled, these subtle ripples became the seeds of everything we see today. Where matter was just slightly denser, gravity began its slow, methodical work of gathering. Hydrogen and helium, the universe's first and simplest elements, started to clump together like cosmic dust bunnies forming in the corners of space. This wasn't a quick process. For hundreds of millions of years, the universe remained dark. No stars had yet ignited, no galaxies had formed. It was a time astronomers poetically call the cosmic dark ages, though it wasn't truly empty. Invisible scaffolding was being built, dark matter weaving itself into a cosmic web that would guide the formation of everything to come. Think of dark matter as the universe's hidden architect. We can't see it directly, can't touch it, can't even detect it with our most sensitive instruments. But its gravitational influence shaped the cosmos like a sculptor working with invisible clay. It formed filaments and nodes, creating a three-dimensional web stretching across billions of light years. At the intersections of these filaments, where the web was thickest, ordinary matter began to accumulate. The first stars were monsters. Population 3 stars, as astronomers call them, were hundreds of times more massive than our sun. They burned hot and fast, living furious lives before exploding in spectacular supernovae or collapsing into black holes. But in their brief existence, they accomplished something extraordinary. They lit up the universe. Their ultraviolet light began ionizing the hydrogen fog that filled space, gradually making the universe transparent. It was like watching fog lift from a landscape at dawn, revealing the hidden architecture beneath. For the first time since the Big Bang's afterglow faded, the universe began to shine. But these stellar giants were more than just cosmic lighthouses. When they died, they scattered the first heavy elements into space: carbon, oxygen, iron, and all the building blocks needed for planets and life. The universe was slowly enriching itself, each stellar death seeding the cosmos with complexity. The first proto-galaxies were nothing like the elegant spirals we see today. They were chaotic, irregular clumps of stars held together by gravity and embedded in massive halos of dark matter. Picture them as cosmic villages, small communities of stars finding each other in the vast darkness. But these villages had ambitions. Gravity continued its patient work, pulling proto-galaxies together, causing them to merge and grow. It was a violent process, with stellar communities crashing into each other in slow-motion collisions that lasted millions of years. Stars were flung across space, gas clouds compressed and heated, triggering bursts of new star formation. Over billions of years, order began to emerge from this chaos. Galaxies that accumulated enough material and had the right amount of rotation flattened into disks. Density waves rippled through these disks, compressing gas and creating the beautiful spiral arms we recognize today. Others, shaped by repeated collisions, settled into the smooth elliptical forms that dominate galaxy clusters. The cosmic web continued to guide this process. Galaxies formed along its filaments like pearls on invisible strings, while vast voids remained nearly empty, dark regions where few stars would ever shine. The universe was organizing itself into the largest structures we know: clusters and superclusters of galaxies, connected by bridges of dark matter spanning hundreds of millions of light years. At the heart of nearly every galaxy, something else was growing: supermassive black holes. These gravitational titans, millions or billions of times the mass of our sun, weren't just passengers in galactic evolution. They were co-authors of the story, regulating star formation through their feeding cycles, shaping the galaxies around them with jets of plasma that could stretch for thousands of light years. Our own Milky Way emerged from this cosmic dance about 13 billion years ago. We live in its suburbs, orbiting a modest yellow star in one of its spiral arms. From our perspective, we see the galaxy edge on as a river of light across the night sky, a reminder that we're embedded within one of the universe's great cities of stars. The Milky Way continues to grow, slowly absorbing smaller satellite galaxies and preparing for its eventual merger with Andromeda, our nearest large neighbor. In about 4 billion years, these two spiral galaxies will dance together, their arms intertwining before settling into a new configuration. It won't be violent on human scales. Stars are too far apart to collide, but it will reshape our corner of the universe entirely. Today, we can see the results of this 13 billion year story written across the sky. Every galaxy we observe through our telescopes represents a different chapter in cosmic evolution. Some are young and irregular, still in their chaotic youth. Others are mature spirals like our own, steadily converting gas into stars. Still others are ancient ellipticals, their star formation long since ended, glowing with the soft red light of an aging stellar population. The story isn't over. Galaxies continue to evolve, merge, and interact. New stars are born in their spiral arms and star-forming regions, while others reach the end of their lives, enriching the interstellar medium with heavy elements. Black holes grow and regulate. The cosmic web continues to guide the flow of matter on the largest scales, and dark energy accelerates the expansion of space itself. But perhaps the most remarkable part of this story is that we're here to tell it. In a small galaxy around an ordinary star on a rocky planet, atoms forged in stellar cores have assembled into beings capable of looking back across billions of years and piecing together their own cosmic origins. We are the universe becoming aware of itself, made of ancient starlight and wondering at the darkness between the stars. Every atom in your body was once inside a star. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were forged in stellar furnaces and scattered by stellar winds and supernovae. You are not just in the universe, you are part of its story, a temporary arrangement of cosmic matter that has learned to contemplate its own existence. As you drift towards sleep tonight, remember that you're riding on a planet orbiting a star in the outer regions of a spiral galaxy, one of hundreds of billions in the observable universe. We've come full circle now, haven't we? From the cosmic dance of galaxies to the intimate waltz of moons around their planets, from the birth of stars in distant nebulae to the quiet pull of tides on our own pale blue dot. Tonight, we find ourselves contemplating something both ancient and immediate. How these celestial companions, these dancing partners in the cosmic ballet, have shaped not just the physics of space, but the very story of life itself. You see, moons are far more than silent observers hanging in our night sky. They are active participants in the grand theater of planetary evolution, choreographers of change, and in many cases, the unsung heroes of habitability itself. Our own moon, that familiar silver disk that has inspired countless poets and dreamers, has been quietly engineering the conditions for life on Earth for over 4 billion years. Consider this. Without our moon, days on Earth would last only about 6 hours. The moon's gravitational embrace acts as a cosmic brake, gradually slowing our planet's rotation through the elegant mechanism of tidal friction. Those same tides that ebb and flow along our coastlines are slowly but persistently transferring Earth's rotational energy to the moon's orbit, causing our satellite to spiral gradually outward while our days grow longer. It's a patient process, this celestial clockwork, unfolding over geological timescales that dwarf human civilization. But the moon's influence extends far beyond timekeeping. That gentle tidal flexing may have been crucial for the emergence of life itself. Picture the early Earth, a world of shallow seas and volcanic shores. The moon's gravitational pull creates tidal pools, those temporary bridges between ocean and land where complex organic molecules could concentrate, interact, and perhaps take their first tentative steps toward self-replication. Some scientists propose that these rhythmic cycles of wetting and drying, orchestrated by our lunar companion, provided the perfect laboratory for life's earliest experiments. The moon also serves as Earth's stabilizing influence, keeping our planet's axial tilt relatively steady over millions of years. Without this gravitational anchor, Earth might wobble chaotically, causing wild climate swings that could make complex life nearly impossible. Mars, lacking such a large, stabilizing moon, experiences dramatic variations in its axial tilt, contributing to its current frozen, inhospitable state. Our moon, it seems, has been keeping Earth's climate within the bounds necessary for life to flourish and evolve. But Earth's moon is just one player in a much grander ensemble. Throughout our solar system, moons reveal themselves as worlds of astonishing complexity and possibility. Take Jupiter's Europa, a moon that has captured the imagination of astrobiologists worldwide. Beneath its icy shell lies an ocean that contains more water than all of Earth's seas combined. This subsurface ocean, kept liquid by the tidal heating generated by Jupiter's immense gravitational pull, represents one of the most promising places to search for life beyond Earth. Europa's ocean has likely existed for billions of years, maintained by the same tidal forces that heat its rocky core and drive hydrothermal activity on its seafloor. On Earth, life thrives around such hydrothermal vents, deriving energy not from sunlight, but from chemical processes. Europa's hidden sea may harbor similar ecosystems, communities of microorganisms that have never seen a star yet flourish in the warm embrace of tidal heating. Saturn's moon Enceladus tells a similar story. This small, ice-covered world shoots towering geysers of water vapor and organic compounds from cracks in its south polar region. These geysers, powered by tidal heating from Saturn's gravity, provide direct evidence of a subsurface ocean and active geology. When the Cassini spacecraft flew through these plumes, it tasted the ingredients for life: water, organic molecules, and energy sources. Enceladus may be small, but it harbors an ocean world that could potentially support life. Then there's Titan, Saturn's largest moon and perhaps the most Earth-like world in our solar system, despite being utterly alien. Titan has lakes and rivers, weather patterns, and seasonal cycles, but instead of water, its hydrological cycle runs on liquid methane and ethane. Dense orange clouds shroud its surface, and beneath its icy crust lies yet another subsurface ocean. Titan represents a fascinating example of how moons can develop complex, Earth-like processes using entirely different chemistry. Even more exotic is Io, Jupiter's innermost large moon, where tidal heating has created the most volcanically active world in the solar system. Io's surface is constantly renewed by sulfur-rich volcanic eruptions, some of which blast material hundreds of kilometers into space. While Io itself is too hostile for life as we know it, its extreme volcanism demonstrates the incredible power of tidal forces to reshape entire worlds. These examples reveal a profound truth. Moons are not merely passive rocks orbiting their planets. They are dynamic, evolving worlds where gravitational forces, orbital mechanics, and planetary physics combine to create environments of startling complexity. The dance between moon and planet generates energy, drives geological processes, and in some cases, creates conditions that could nurture life. This brings us to one of the most elegant concepts in planetary science: orbital resonance. Many moons are locked in gravitational relationships that create recurring patterns, like Jupiter's three largest moons, Io, Europa, and Ganymede. For every 4 orbits Io completes, Europa completes exactly 2, and Ganymede completes exactly 1. This precise celestial choreography, maintained over billions of years, pumps energy into these worlds through tidal heating, powering the geological processes that make them such fascinating places. The story of moons is ultimately a story about connection, about how celestial bodies influence each other across vast distances through the invisible threads of gravity. It's about how the universe creates complexity from simplicity, how the interplay of mass and distance and time can sculpt worlds, and perhaps even nurture life. As we look toward the future of space exploration, moons have become prime targets for astrobiology missions. Spacecraft are being designed to land on Europa and Enceladus, to drill through their ice shells and taste their hidden oceans directly. We may soon answer one of humanity's most profound questions. Are we alone? And if we find life in these distant ocean worlds, it will likely be thanks to the same tidal forces that have shaped our own planet for billions of years. But perhaps the most remarkable thing about moons is how they remind us of our cosmic context. Every time you see the moon rise over the horizon, you're witnessing a gravitational ballet that has been playing out since the solar system was young. That same moon that pulls our tides once helped establish the conditions that allowed life to emerge and evolve on Earth. The moonlight that illuminates your evening walk is reflected sunlight that has traveled across the void to touch a world that has been our planet's faithful companion for eons. So as you drift toward sleep tonight, carried along by Earth's rotation as our planet spins beneath the watchful gaze of its ancient lunar partner, remember that you are part of this cosmic dance. The atoms in your body were forged in the hearts of stars. The water in your cells may have arrived on comets from the outer solar system, and the very rhythm of your days has been set by the gravitational embrace between our world and its moon. The secret lives of planetary satellites are really the secret lives of worlds in conversation, celestial bodies speaking to each other in the language of gravity and time. They are the universe's way of showing us that no world is truly alone, that even across the vast emptiness of space, connections persist, influences flow, and the dance goes on. Sweet dreams, fellow traveler. Hello there and welcome to the Sleepy Scientist, where curiosity meets calm and we explore the vast wonders of our universe together. Before we begin tonight's gentle journey through the cosmos, I'd love to know where in the world you're listening from. There's something beautifully poetic about how we're all connected across different time zones, different hemispheres, yet united under the same star-filled sky. If you find tonight's voyage through space soothing or intriguing, I'd be ever so grateful if you gave this video a gentle like or perhaps subscribe to join our community of cosmic wanderers. It helps more sleepy minds find their way to these quiet corners of scientific wonder. Now tonight we're continuing our exploration of planetary satellites, those fascinating celestial dancers that orbit the worlds of our solar system. We've already discovered how moons are born from cosmic collisions and gravitational captures, how they perform intricate orbital ballets, and how they shape the very worlds they circle. But there's so much more to uncover about these remarkable companions. Tonight, we'll delve deeper into the secret lives of moons, exploring how they create the conditions for life itself, how they sculpt planetary rings into works of cosmic art, and how they serve as time capsules, preserving the ancient history of our solar system in their scarred and cratered faces. We often think of moons as simple, unchanging orbs hanging in the night sky, but the reality is far more dynamic and surprising. These celestial bodies are active participants in a grand cosmic symphony, influencing everything from the tides in our oceans to the stability of planetary climates across the solar system. Consider for a moment the remarkable relationship between our Earth and its moon. This partnership, forged in violence billions of years ago when a Mars-sized object crashed into our young planet, has become one of the most stabilizing forces in our solar system. Without our moon's gravitational embrace, Earth would wobble chaotically on its axis, creating wild climate swings that would make complex life nearly impossible. But our moon does far more than just steady our planet's rotation. It acts as a cosmic choreographer, orchestrating the rise and fall of our oceans twice each day. These tidal forces don't just move water. They've shaped the very evolution of life on our planet. The rhythmic exposure of coastal areas during low tide may have provided the perfect laboratory for early life forms to transition from sea to land, making the moon an unsung hero in the story of terrestrial evolution. The moon's influence extends beyond biology into geology itself. As our planet spins within the moon's gravitational field, the solid Earth actually flexes and stretches, rising and falling by several inches each day. This constant kneading helps drive plate tectonics, the slow dance of continents that recycles carbon and maintains our planet's stable climate over geological timescales. Yet Earth's moon, remarkable as it is, represents just one chapter in the vast library of satellite stories throughout our solar system. Journey outward to Jupiter, and we encounter a system of moons so diverse and dynamic that each one reads like a different genre of planetary science. Io, the innermost of Jupiter's 4 largest moons, exists in a state of constant volcanic fury. Caught in a gravitational tug-of-war between Jupiter and its neighboring moons Europa and Ganymede, Io experiences tidal forces so intense that its interior remains molten. The result is a world painted in sulfur yellows and volcanic reds, where towering plumes of material erupt hundreds of kilometers into space. Io is the most volcanically active body in our solar system, reshaping its surface so rapidly that impact craters barely have time to form before being erased by fresh lava flows. Moving outward, we encounter Europa, perhaps the most intriguing moon in our solar system from the perspective of astrobiology. Beneath its icy shell lies an ocean that may contain more than twice as much water as all of Earth's oceans combined. This subsurface sea, kept liquid by the same tidal heating that drives Io's volcanoes, represents one of the most promising places to search for life beyond Earth. The evidence for Europa's hidden ocean comes from multiple sources. The Galileo spacecraft detected magnetic field signatures consistent with a conducting fluid beneath the ice. The moon's surface shows clear signs of geological activity, with linear features called lineae that appear to be cracks in the ice shell, possibly formed as the ocean below expands and contracts with tidal forces. But Europa's ocean isn't just a static body of water. Recent observations suggest it may have active hydrothermal vents on its seafloor, similar to those found in Earth's deep oceans. These underwater volcanic features could provide the chemical energy needed to support life, creating oases of biological activity in the cold darkness beneath Europa's ice. The possibility of life in Europa's ocean has captured the imagination of scientists and the public alike. Unlike the surface of Mars, which is bathed in sterilizing radiation, Europa's ocean is protected by kilometers of ice, creating a stable environment that has persisted for billions of years. If life exists there, it would represent a completely independent genesis of biology, proving that life can arise wherever the right conditions persist. Continuing our journey through Jupiter's satellite system, we arrive at Ganymede, the largest moon in our solar system. Ganymede is remarkable not just for its size, it's larger than the planet Mercury, but for its complex internal structure. Like Europa, Ganymede harbors a subsurface ocean, but this one exists in a more complex layered system, with multiple levels of ice and water stacked like a geological sandwich. Ganymede also holds the distinction of being the only moon in our solar system known to generate its own magnetic field. This magnetosphere, created by the motion of conducting fluids in Ganymede's core, provides additional evidence for the moon's active interior and complex structure. Then there's Callisto, the most heavily cratered object in our solar system, its ancient surface preserving a record of the violent early history of the solar system. Unlike its more dynamic siblings, Callisto appears to be a relatively unchanged world, a museum of impact scars that tells the story of the late heavy bombardment, a period roughly 4 billion years ago when asteroids and comets rained down upon the inner solar system. Yet even Callisto may harbor secrets beneath its battered exterior. Recent studies suggest that this ancient moon, too, may contain a subsurface ocean, making Jupiter's system a collection of hidden seas beneath icy shells. The story becomes even more remarkable when we consider Saturn's family of moons. Here we find Enceladus, a small icy world that has revolutionized our understanding of where life might exist in the cosmos. Despite being only about 500 kilometers in diameter, roughly the width of Arizona, Enceladus hosts one of the most spectacular displays in the solar system. From cracks near its south pole, called tiger stripes, Enceladus shoots enormous plumes of water vapor and ice particles hundreds of kilometers into space. These geysers, first discovered by the Cassini spacecraft, provide direct evidence of a subsurface ocean and offer a tantalizing opportunity to sample that hidden sea without having to drill through kilometers of ice. Analysis of material from these plumes has revealed not just water, but also organic compounds and even tiny rock particles from the moon's seafloor. The chemistry suggests that Enceladus's ocean is in contact with rock, potentially creating the same kind of hydrothermal systems that may have given rise to life on early Earth. The energy driving Enceladus's activity comes from tidal heating, just like on Io and Europa, but the source is more complex. The moon's eccentric orbit, maintained by gravitational resonances with other Saturnian moons, causes its interior to flex and heat as it travels around Saturn. This process has kept Enceladus's ocean liquid for potentially billions of years, creating a stable environment where life might have had time to evolve. But perhaps the most alien of all moons is Titan, Saturn's largest satellite and the second largest moon in the solar system. Titan is the only moon with a substantial atmosphere, one that's actually denser than Earth's. This thick blanket of nitrogen and methane creates weather patterns, seasonal cycles, and even a hydrological cycle, though one based on liquid hydrocarbons rather than water. Titan's surface, hidden beneath its opaque atmosphere, remained a mystery until the Cassini mission and its Huygens probe finally pierced the veil. What they revealed was a world that bears a startling resemblance to early Earth, complete with rivers, lakes, and seas. But instead of water, these features are filled with liquid methane and ethane, creating an alien landscape where it rains gasoline under an orange sky. The Huygens probe, which successfully landed on Titan's surface, found a world of rounded ice pebbles and hydrocarbon sand dunes. The landscape showed clear evidence of erosion and sediment transport, processes driven by Titan's methane weather systems. In many ways, Titan represents a parallel development of planetary processes, showing us how familiar geological and meteorological phenomena can operate in completely alien chemical environments. Beneath Titan's hydrocarbon lakes and icy crust lies yet another subsurface ocean, this one composed of liquid water mixed with ammonia, which acts as antifreeze to keep the ocean liquid at Titan's frigid temperatures. This hidden sea may be another potential habitat for life, though any organisms there would be completely isolated from the exotic chemistry happening on the moon's surface. The diversity of environments found among just these few moons highlights one of the most important discoveries of modern planetary science. the concept of habitable zones needs to be completely reconsidered. We once thought that life required a planet to orbit within a narrow band around its star, where temperatures would allow liquid water to exist on the surface. But the moons of the outer solar system have shown us that tidal heating can create habitable environments far from the sun's warmth. This revelation has profound implications for the search for life beyond our solar system. If moons around giant planets can harbor life, then the number of potentially habitable worlds in the galaxy increases dramatically. Every star system with gas giant planets becomes a potential host for multiple worlds where life might arise. The gravitational relationships that make these hidden oceans possible also create some of the most complex and beautiful orbital dynamics in the solar system. The Galilean moons of Jupiter, for instance, are locked in a precise gravitational dance called a Laplace resonance. For every orbit that Ganymede completes around Jupiter, Europa completes exactly 2, and Io completes exactly 4. This isn't coincidence, but the result of millions of years of gravitational evolution, where the moons have gradually settled into this stable, harmonious arrangement. These orbital resonances do more than create mathematical elegance. They're the engines that drive geological activity throughout the Jupiter system. The gravitational tugs and pulls between the moons constantly stretch and squeeze their interiors, generating the heat that keeps oceans liquid and volcanoes active. Without these resonances, the moons would be cold, dead worlds, their interiors frozen solid. Similar resonances exist throughout the solar system, from the 2-1 resonance between Neptune and Pluto to the complex orbital relationships among Saturn's many small moons. These gravitational partnerships show us that the solar system isn't just a collection of independent objects, but an integrated system where each world influences and is influenced by its neighbors. The study of these resonances has also revealed the dynamic history of our solar system. The current arrangement of planets and moons isn't the one they started with. Over billions of years, gravitational interactions have caused planets to migrate, moons to spiral inward or outward, and entire systems to reorganize themselves. The NICE model, one of the leading theories of solar system evolution, suggests that the giant planets once underwent a period of dramatic orbital migration, reshuffling the entire architecture of the outer solar system and triggering the late heavy bombardment that scarred the surfaces of the inner planets and moons. Evidence for this ancient migration comes from many sources, including the current orbital characteristics of asteroids and comets, the unusual rotation of Uranus, and the orbital properties of Neptune's largest moon, Triton. Triton, which orbits Neptune backward compared to the planet's rotation, is almost certainly a captured Kuiper Belt object, a dwarf planet that was gravitationally seized during Neptune's migration outward. The capture of Triton would have been a catastrophic event for Neptune's original moon system. The large retrograde moon would have gravitationally disrupted the orbits of Neptune's other satellites, possibly destroying many of them in collisions or ejecting them from the system entirely. This violent history is preserved in Neptune's current satellite system, which consists mainly of small, irregular moons, in addition to the dominant Triton. These stories of capture, collision, and migration remind us that the solar system we see today is the survivor of a much more chaotic past. The moons that orbit planets today are the remnants of larger populations that were sculpted by billions of years of gravitational evolution. Each satellite system tells a unique story of formation, evolution, and survival in the gravitational furnace of the early solar system. The rings that grace several of the giant planets provide another window into these dynamic processes. Saturn's magnificent ring system, visible even through small telescopes, is thought to be relatively young in astronomical terms, perhaps only a few 100 million years old. These rings may be the debris from a destroyed moon, torn apart when it wandered too close to Saturn and crossed the Roche limit, the point where tidal forces overcome a body's own gravity. The process of ring formation and evolution is ongoing. Saturn's rings are constantly being sculpted by the gravitational influence of nearby moons, which create gaps, waves, and intricate structures within the ring material. The Cassini division, the prominent gap in Saturn's rings, is maintained by a gravitational resonance with the moon Mimas. Particles in the gap would complete exactly 2 orbits for every 1 orbit of Mimas, and this resonance eventually ejects them from that region. Other moons act as shepherds, using their gravity to confine ring particles to narrow bands. The F ring, Saturn's outermost main ring, is kept in place by 2 small moons, Prometheus and Pandora, which orbit just inside and outside the ring, respectively. These shepherd moons occasionally create dramatic disturbances in the ring material, producing kinked and braided structures that change over timescales of months or years. Jupiter, Uranus, and Neptune also have ring systems, though much fainter than Saturn's spectacular display. These rings are also maintained by the gravitational influence of nearby moons, showing that the relationship between rings and satellites is a fundamental aspect of giant planet systems. The study of ring-moon interactions has provided crucial insights into how planetary systems form and evolve. The same processes that create gaps in Saturn's rings may have operated during the formation of our solar system, helping to clear the spaces between planetary orbits and concentrate material into the zones where planets could grow. As we contemplate these vast scales of space and time, it's humbling to realize that we're witnessing just a brief moment in the ongoing evolution of our solar system. The moons we observe today are temporary arrangements, constantly changing as they spiral toward or away from their parent planets, as tidal forces gradually synchronize their rotations, and as the subtle influence of solar radiation pressure and other effects alter their orbits. 8 centimeters per year. This recession is caused by tidal friction, the same force that has synchronized the moon's rotation with its orbit, ensuring that the same hemisphere always faces Earth. Billions of years from now, if the sun doesn't interfere first, the Earth-Moon system will become tidally locked, with both bodies showing the same face to each other as they orbit their common center of mass. This process of tidal evolution has already played out in many other satellite systems. Most of the major moons in the solar system are tidally locked to their parent planets, from our own moon to the Galilean satellites of Jupiter to Saturn's largest moons. This synchronization is not just a curiosity, but has profound implications for these worlds' geology and potential habitability. Tidal locking creates permanent day and night hemispheres, leading to extreme temperature differences that can drive atmospheric circulation and weather patterns. On Titan, for example, the slight temperature difference between the hemisphere that faces Saturn and the one that faces away helps drive the global circulation of methane clouds and weather systems. For moons with subsurface oceans, tidal locking affects how heat is distributed within their interiors. The constant flexing of these worlds as they orbit their parent planets in elliptical paths creates hotspots and thermal gradients that may be crucial for maintaining liquid water and driving chemical processes that could support life. The search for life in these hidden oceans has become one of the most exciting frontiers in astrobiology. Future missions are already in development to explore these distant seas. NASA's Europa Clipper mission, scheduled to launch in the 2020s, will make detailed studies of Europa's ice shell and subsurface ocean. ESA's JUICE mission will explore Jupiter's system with a focus on Ganymede, while other proposed missions would send landers or even submarines to explore these alien seas directly. The technical challenges of exploring subsurface oceans are immense. Any probe would need to survive the journey to the outer solar system, land on an icy surface in extremely cold conditions, then somehow penetrate kilometers of ice to reach the ocean below. But the potential rewards are equally immense. The discovery of life in these hidden seas would revolutionize our understanding of biology and our place in the universe. Even if life doesn't exist in these oceans today, they may preserve evidence of past biological activity. The organic compounds detected in Enceladus's plumes and the complex chemistry observed on Titan show that the raw materials for life are abundant in the outer solar system. Understanding how these materials interact and evolve could provide crucial insights into how life might arise in similar environments around other stars. The moons of the outer solar system also serve as natural laboratories for studying extreme physics and chemistry. The radiation environment around Jupiter is so intense that it would be lethal to humans within minutes. Yet Io and Europa orbit within this maelstrom of charged particles. Understanding how these moons survive and even thrive in such conditions could inform our understanding of how planets around other stars might cope with the radiation from their host stars. The low-gravity environments on these moons also create unique conditions that don't exist on Earth. On Titan, the combination of low gravity and thick atmosphere means that humans could potentially fly with simple wing-powered aircraft. The reduced gravity also affects how liquids behave, creating unique erosion patterns and geological processes that we're only beginning to understand. These alien physics become especially important when we consider the possibility of human exploration of the outer solar system. While the distances are vast and the challenges enormous, the resources available on these moons could potentially support future human settlements. The water ice that makes up much of these worlds could be broken down into hydrogen and oxygen for fuel and life support, while the organic compounds on worlds like Titan might provide raw materials for manufacturing. The energy sources that keep these moons active, from tidal heating to radioactive decay, could potentially be harnessed to power human operations. Io's volcanic activity, while dangerous, represents an enormous energy source. Europa's subsurface ocean might be tapped not just for water, but as a thermal reservoir for generating power. But perhaps the most important resource these moons offer is knowledge. Each world represents a unique experiment in planetary evolution, showing us how different combinations of size, composition, and orbital characteristics lead to different outcomes. By studying this diversity, we learn about the fundamental processes that shape all worlds, including our own. The irregular moons that orbit the giant planets in distant, tilted orbits provide insights into the early bombardment history of the solar system. Many of these small worlds are probably captured asteroids or comets, and their surfaces preserve records of impact events that occurred billions of years ago. By studying their crater populations and compositions, we can learn about the population of impactors that shaped the early solar system and understand the processes that delivered water and organic materials to the inner planets. Some of these irregular moons show signs of past geological activity despite their small sizes. Iapetus, one of Saturn's mid-sized moons, has a mysterious equatorial ridge that gives it a walnut-like appearance. This feature, along with Iapetus's two-toned coloration, suggests a complex history that we're still working to understand. The small moons embedded within the ring systems of the giant planets tell stories of accretion and destruction played out on rapid timescales. These moonlets, some only kilometers across, are constantly being created and destroyed as ring particles clump together or are torn apart by tidal forces. They provide real-time examples of the processes that may have operated during the formation of larger moons and planets. Pan and Daphnis, two small moons that orbit within Saturn's rings, have created distinctive propeller-shaped disturbances in the ring material. These features, visible in high-resolution images from Cassini, show how even tiny gravitational perturbations can create large-scale structures in disk systems. Similar processes may have operated in the disk of material from which our solar system formed, helping to concentrate matter and create the building blocks of planets. The co-orbital moons, Janus and Epimetheus, which share nearly identical orbits around Saturn, perform a unique gravitational dance. Every few years, the inner moon catches up to the outer one, and they exchange orbits through a complex gravitational interaction. This horseshoe orbit configuration may be more common than once thought, and could help explain some of the puzzling characteristics of asteroid and comet populations. These intricate orbital relationships demonstrate that the solar system is far from the simple clockwork mechanism that early astronomers imagined. Instead, it's a dynamic, ever-changing system where small perturbations can have large consequences, and where the seemingly stable orbits we observe today are the result of billions of years of gravitational evolution. The study of satellite systems around other planets in our solar system has also informed our understanding of exoplanet systems. Many of the planets discovered around other stars are gas giants that orbit very close to their host stars, unlike anything in our solar system. Understanding how the moons of Jupiter and Saturn behave helps us predict what kinds of satellite systems these hot Jupiters might have, and whether those moons could be habitable despite their proximity to their stars. The techniques developed to study the moons of our solar system are now being applied to search for exomoons, moons orbiting planets around other stars. While no exomoons have been definitively confirmed yet, several candidates have been identified, and future space telescopes should be able to detect moons around nearby exoplanets. The diversity of satellite systems in our own solar system suggests that exomoons should be common and varied. Some might be larger than Earth, orbiting super-Jupiter planets in the habitable zones of their stars. Others might be small, airless worlds like our own moon, but orbiting in very different environments. Each type of exomoon system would create different possibilities for habitability and life. As we continue to explore the moons of our solar system with increasingly sophisticated instruments, we're constantly surprised by their complexity and diversity. Every new mission reveals unexpected phenomena, from the active geology of small icy moons to the complex atmospheric chemistry of Titan to the intricate ring-moon interactions around Saturn. The James Webb Space Telescope, with its unprecedented infrared capabilities, is beginning to provide new insights into the compositions and atmospheres of solar system moons. Its ability to detect trace gases and organic compounds could reveal new information about the chemistry of Titan's atmosphere and the composition of material ejected from Enceladus's plumes. Future missions will push the boundaries even further. Concepts under study include nuclear-powered probes that could operate in the outer solar system for decades, advanced rovers that could explore multiple moons during single missions, and even aerial vehicles that could fly through Titan's thick atmosphere or investigate the plumes of Enceladus from close range. The technological challenges of exploring these distant worlds drive innovation that benefits life on Earth as well. The extreme conditions encountered by spacecraft in the outer solar system require advances in materials science, power systems, and autonomous navigation that find applications in terrestrial technology. The techniques developed to search for life in subsurface oceans could help us better understand and explore Earth's own deep biosphere. But perhaps the most profound impact of studying these moons is philosophical. They've expanded our concept of habitability far beyond the narrow zone around stars, where liquid water can exist on planetary surfaces. The realization that warm, wet environments might exist throughout the cosmos, hidden beneath the icy shells of moons around giant planets, suggests that life might be far more common than we ever dared hope. This expansion of possibilities comes at a crucial time in human history, as we develop the technological capabilities to seriously search for life beyond Earth. The moons of our solar system provide nearby laboratories where we can test our theories about biology, develop our exploration techniques, and refine our understanding of what signatures of life to look for in the cosmos. As you drift toward sleep tonight, perhaps you'll dream of sailing through the subsurface seas of Europa, watching geysers erupt on Enceladus, or soaring through Titan's orange skies. These aren't just fantasies, but possible futures, as humanity gradually extends its reach into the solar system and beyond. The moons that dance around the planets of our solar system are more than just points of light in the night sky. They're worlds in their own right, each with unique stories to tell about the formation and evolution of planetary systems. They're potential harbors for life, resources for future exploration, and windows into the fundamental processes that shape all worlds. In their orbital dances, we see the elegant mathematics of gravity played out on cosmic scales. In their geological activity, we witness the power of tidal forces to reshape entire worlds. In their hidden oceans and exotic atmospheres, we glimpse possibilities for life that we're only beginning to understand. The secret lives of these planetary satellites remind us that the universe is far stranger and more wonderful than our earthbound experience might suggest. Every world is an experiment in physics and chemistry, showing us new ways that matter and energy can organize themselves into complex, beautiful, and potentially living systems. As our exploration of these distant moons continues, we're not just learning about other worlds, but about our own place in the cosmic story. We're discovering that Earth and its moon are part of a vast family of planet-satellite systems, each unique but all connected by the fundamental forces that govern the universe. So rest easy tonight, knowing that high above, the moon continues its ancient dance around Earth, stabilizing our planet's climate and driving the tides that shaped the evolution of life. And far beyond, in the cold reaches of the outer solar system, other moons are dancing their own gravitational ballets, harboring hidden oceans, active volcanoes, and perhaps even life itself. The universe is vast and full of wonders, and in the gentle rhythm of celestial mechanics, we find a kind of cosmic lullaby that has been playing since the dawn of time. Beyond our solar system, the story of moons becomes even more intriguing. As astronomers discover thousands of exoplanets orbiting distant stars, we're beginning to realize that many of these worlds likely have their own families of satellites. Some of these exomoons might be larger than Earth itself, massive worlds with thick atmospheres and complex weather systems orbiting gas giants in the habitable zones of their stars. Imagine, if you will, a moon the size of our planet, but orbiting a Jupiter-like world that sits at just the right distance from its star for liquid water to exist. Such a moon would experience a day-night cycle determined not by its orbit around the star, but by its orbit around its parent planet. It might have magnificent auroras as charged particles from its planet's magnetosphere interact with its atmosphere. Its skies would be dominated by the looming presence of its giant parent world, creating spectacular eclipses and tidal effects far more dramatic than anything we experience on Earth. The search for these exomoons represents one of the next great frontiers in astronomy. While detecting planets around other stars has become almost routine, finding their moons requires extraordinary precision. We must look for the tiny gravitational wobbles that moons induce in their parent planets, or the subtle dimming of starlight when both planet and moon pass in front of their star. Several promising exomoon candidates have been identified, though none have been confirmed with certainty. The techniques are improving rapidly, and within the next decade, we may have our first definitive detection of a moon around an exoplanet. That discovery would open an entirely new chapter in our understanding of planetary systems and the potential for life in the universe. But let's return for a moment to our own cosmic neighborhood, where the moons continue to surprise us with their hidden complexities. Recent discoveries have shown that even the smallest satellites can harbor unexpected geological activity. Mimas, one of Saturn's smaller moons, long thought to be a dead, cratered world, may actually contain a subsurface ocean of its own. If confirmed, this would make Mimas one of the smallest bodies in the solar system known to have liquid water, suggesting that such hidden seas might be even more common than we currently realize. The implications are staggering. If tiny Mimas can maintain a liquid ocean, then perhaps dozens of other small icy moons throughout the outer solar system are doing the same. Each would represent a potential habitat for life, a hidden biosphere existing in darkness beneath kilometers of ice. The number of potentially habitable worlds in our solar system alone could number in the dozens. This abundance of liquid water in unexpected places has revolutionized astrobiology. We once searched for life by looking for planets in the Goldilocks zone around stars, where temperatures are just right for surface water. Now we realize that most of the liquid water in the universe might exist in hidden oceans, warmed not by starlight, but by the gentle kneading of gravitational forces. These discoveries have also changed how we think about the ingredients necessary for life. On Earth, life depends on the energy from our sun, either directly through photosynthesis or indirectly through the food webs that photosynthesis supports. But in the hidden oceans of icy moons, life would need to rely on chemical energy, perhaps from hydrothermal vents on the seafloor, or from the breakdown of organic compounds in the water. Such chemosynthetic ecosystems do exist on Earth, thriving around deep-sea hydrothermal vents and in other extreme environments where sunlight never penetrates. These communities, based on bacteria that can extract energy from chemical reactions rather than sunlight, show us that life can flourish in the absence of photosynthesis. They provide a template for what life might look like in the dark oceans of Europa, Enceladus, and their kin. The chemistry of these hidden seas is another source of fascination. On Earth, our oceans are salty, filled with dissolved minerals that have been weathered from rocks over billions of years. The subsurface oceans of icy moons likely have their own unique chemistries, influenced by the composition of their rocky cores and the processes that maintain their liquid state. Enceladus's ocean, for example, appears to be alkaline, with a pH similar to that of household ammonia. This chemistry is created by the interaction of liquid water with the moon's rocky core, a process called serpentinization that releases hydrogen gas and creates conditions that could support certain types of life. On Earth, similar chemical processes in underwater rock formations provide energy for. We've journeyed through the birth pangs of galaxies, watched the first stars ignite in cosmic darkness, and explored the elegant spiral arms of our own Milky Way. We've seen how gravity, dark matter, and supermassive black holes work together as invisible architects, shaping the grand structures that fill our universe. From ancient light carrying messages across billions of years to the ongoing cosmic dance of galactic collisions and mergers, we've traced the story of how scattered hydrogen became the magnificent cities of stars we see today. But our exploration doesn't end with distant galaxies. The cosmic web continues to evolve, and new discoveries await us at every turn. Scientists are pushing the boundaries of what we can observe, using increasingly sophisticated instruments to peer deeper into space and further back in time. The James Webb Space Telescope has already begun revolutionizing our understanding of early galaxy formation, revealing surprisingly mature structures in the infant universe and challenging our models of cosmic evolution. Perhaps most remarkably, we're beginning to understand that the formation of galaxies is intimately connected to the emergence of complexity itself. The heavy elements forged in stellar cores and scattered by supernovae didn't just enrich the interstellar medium, they made possible the formation of rocky planets, complex chemistry, and ultimately, life itself. Every atom in your body, save for hydrogen, was created in the nuclear furnaces of stars that lived and died before our solar system even existed. Looking ahead, the universe's story is far from over. While we're entering a more sedate era of cosmic evolution, with star formation rates declining and many galaxies settling into quiet maturity, new chapters are still being written. Future galactic mergers will reshape local neighborhoods of the cosmos, and the ongoing expansion driven by dark energy will eventually isolate galaxy clusters from one another, creating island universes drifting alone in an ever-expanding sea of space. As we stand on our small world, gazing up at the star-filled sky, we're witnessing the result of nearly 14 billion years of cosmic evolution. Those distant points of light aren't just pretty decorations scattered across the heavens. They're the visible markers of a vast, interconnected story of matter organizing itself into ever more complex and beautiful forms. We are, quite literally, the universe becoming conscious of itself, using instruments and imagination to understand our own cosmic origins. The story of planetary satellites unfolds like a cosmic ballet of gravitational choreography, where massive worlds gather their smaller companions in a dance that has shaped the very conditions for life. As we've seen, moons are far more than mere ornamental dots in our night sky. They are active geological worlds, potential harbors for life, and the gravitational conductors that orchestrate the rhythms of entire planetary systems. From the tidally heated furnaces of Io to the subsurface oceans of Europa and Enceladus, from the methane lakes of Titan to the shepherding influence of Saturn's ring moons, these satellites reveal themselves as complex, dynamic worlds in their own right. Their interactions create resonances that stabilize orbits, generate internal heat, and maintain the delicate balance between chaos and order that characterizes our solar system. The Moon, our own celestial partner, stands as perhaps the most profound example of this influence. Its gravitational embrace stabilizes Earth's axial tilt, creating the steady seasons that allowed complex life to flourish. Its tidal forces stirred the primordial oceans, possibly providing the energy needed for the first organic molecules to organize themselves into living systems. Without our moon, Earth might be a barren, chaotic world, tumbling through space with wildly varying seasons and no complex life to witness the cosmic dance above. But the influence of moons extends far beyond our own neighborhood. In the outer solar system, where sunlight barely whispers across frozen landscapes, tidal heating becomes the primary source of energy for geological activity. This process, born from the gravitational tug-of-war between planet and satellite, creates environments that might support life in ways we never imagined possible. Beneath kilometers of ice, oceans may teem with possibility, heated not by a distant star, but by the endless gravitational massage of orbital mechanics. The resonances that lock satellites in their cosmic rhythm tell a story of stability emerging from chaos. These gravitational harmonies, like celestial music, ensure that moons maintain their positions over geological time, creating the long-term stability necessary for oceans to persist and life to potentially emerge. The Galilean satellites of Jupiter, locked in their precise dance, demonstrate how multiple worlds can move together in perfect synchronization, each supporting the others in an eternal gravitational embrace. As we peer deeper into space, discovering exoplanets and their potential moon systems, we begin to understand that this dance of satellites may be a universal feature of planetary systems. The moons we see in our solar system may represent just one movement in a vast cosmic symphony, played out around countless stars throughout the galaxy. Each system may have its own unique choreography, its own balance of forces, its own potential for creating the conditions necessary for life. The satellites of our solar system serve as both laboratory and inspiration, showing us how gravitational interactions can sculpt worlds, generate energy, and maintain the delicate conditions that make complex chemistry possible. They remind us that in the cosmic dance of gravity and motion, even the smallest participants can play the most crucial roles, guiding the destiny of entire worlds through their persistent, patient influence. Tonight, as you drift towards sleep, remember that you are part of this grand celestial dance. The moon above continues its ancient orbit, gently tugging at Earth's oceans and maintaining the steady rhythm that has cradled life for billions of years. Somewhere in the outer darkness, the moons of Jupiter and Saturn continue their intricate orbital ballet, their subsurface oceans quietly harboring possibilities we are only beginning to imagine. The secret lives of planetary satellites continue to unfold around us, a reminder that in the vast cosmos, companionship and influence often come from the most unexpected places. In the gentle gravitational whisper between world and moon, in the tidal forces that warm distant oceans, in the orbital resonances that maintain cosmic order, we find the hidden architecture that makes life itself possible. Hello there, and welcome to The Sleepy Scientist, where curiosity meets calm and the cosmos gently rocks you toward slumber. Tonight, we're embarking on a very special journey, one that takes us not just across the universe, but into the secret lives of its most fascinating companions, the moons that dance with their planets in an endless celestial ballet. Before we drift into the depths of space, I'd love to know where in the world you're listening from tonight, and what time it is in your corner of the cosmos. There's something beautifully fitting about a video on planetary satellites, bringing together listeners scattered across time zones, each of us like a small moon in orbit around this shared moment of wonder. If you find tonight's voyage soothing, enlightening, or simply a peaceful way to unwind after the day's earthly concerns, I'd be ever so grateful if you gave this video a gentle like and perhaps subscribed. It helps other stargazers find their way to this quiet corner of the universe. Now, I do hope this isn't so fascinating that it keeps you awake. But if it does, well, at least you'll drift off knowing something extraordinary about the hidden architects of our solar system and beyond. So settle in, let your breathing slow, and prepare to discover that moons are far more than silent, cratered companions. They are sculptors of worlds, guardians of life, and keepers of cosmic secrets, that stretch back to the very birth of planets themselves. In the grand theater of space, we often think of planets as the stars of the show, brilliant performers commanding center stage under the spotlight of their parent stars. But tonight, we turn our attention to the supporting cast, those quiet, often overlooked companions that have been shaping the cosmic drama since the very beginning. The moons, or as astronomers prefer to call them, planetary satellites. These celestial partners are far from mere backup dancers in the cosmic ballet. They are active participants, choreographers even, sculpting the very worlds they orbit through forces both subtle and profound. From our own moon, which has been humanity's faithful nighttime companion since we first gazed upward in wonder, to the icy ocean worlds orbiting Jupiter and Saturn, these satellites hold secrets that could reshape our understanding of life itself. Consider for a moment how different our world would be without the moon's gentle influence. Our days would be mere 6 hours long, spinning past in a blur of shortened seasons and chaotic weather. The tides that have shaped our coastlines, influenced evolution, and inspired countless poets would be reduced to barely perceptible whispers. The very axis of our planet would wobble unpredictably, sending climate patterns into wild fluctuations that might have prevented complex life from ever gaining a foothold. But Earth's moon is just one member of an extraordinary ensemble cast. In the outer reaches of our solar system, moons like Europa, Enceladus, and Titan harbor more liquid water than all of Earth's oceans combined, hidden beneath shells of ice that glitter like jewels in the distant sunlight. These worlds experience tidal heating, a gentle cosmic massage from their giant planet hosts that keeps their buried oceans liquid and perhaps, just perhaps, alive with possibilities we're only beginning to imagine. The story of moons begins in violence and chaos. In the early days when our solar system was a turbulent nursery of colliding rocks and swirling gas, some moons formed alongside their planets from the same cosmic dust, growing up together like siblings sharing the same stellar household. Others were captured wanderers, asteroids and small planets that strayed too close to a larger world's gravitational embrace and found themselves swept into eternal orbit. Our own moon likely came into being through one of the most dramatic origin stories in the solar system. Born from the debris of a Mars-sized object that struck the young Earth in a collision so catastrophic, it briefly turned our planet into a molten hellscape. From that cosmic catastrophe emerged the partnership that would make Earth a cradle for life, as the newly formed moon began its patient work of stabilizing our world's rotation and stirring our primordial oceans. But not all moons are content to orbit peacefully at a safe distance. Some dance so close to their planets that they're slowly being torn apart by tidal forces, their rocky bodies stretched and compressed until they surrender their substance to form magnificent ring systems. Saturn's rings may be the remnants of a moon that ventured too close to its giant host, while Mars's tiny moon Phobos is racing toward a similar fate, spiraling inward and destined to either crash into the red planet or break apart into a ring system of its own within the next 50 million years. Others swing through space on highly elliptical orbits, their surfaces alternately baking and freezing as they journey from close encounters with their planets to lonely sojourns in the cold outer reaches of their orbital paths. These eccentric wanderers often bear the scars of their tumultuous journeys, their surfaces cracked and resurfaced by the constant tug-of-war between gravitational forces. The moons of the gas giants reveal perhaps the most intriguing chapters in this cosmic story. Jupiter's 4 largest satellites, discovered by Galileo over 4 centuries ago, each tell a different tale of planetary formation and evolution. Io, the innermost, is caught in such a fierce gravitational grip between Jupiter and its neighboring moons that its surface is constantly erupting with sulfur volcanoes, making it the most geologically active body in the solar system. Europa glides serenely in its orbit, its smooth ice surface hiding an ocean that may contain twice as much water as all of Earth's seas. Further out, Ganymede reigns as the largest moon in the solar system, bigger even than the planet Mercury, while Callisto bears the scars of billions of years of cosmic bombardment, its ancient surface a museum of solar system history written in craters and impact basins. Saturn's family of satellites is no less remarkable, crowned by Titan, a world shrouded in thick orange clouds that hide lakes and rivers of liquid methane and ethane. Here is a place where the familiar processes of Earth, the water cycle, the formation of rivers and coastlines, play out in an alien chemistry that transforms our understanding of what makes a world dynamic and interesting. And hidden among Saturn's smaller moons, little Enceladus surprised scientists by revealing itself as one of the most promising places to search for life beyond Earth, with geysers of water vapor and organic compounds erupting from cracks in its south polar region, painting a picture of a subsurface ocean in contact with a rocky core where hydrothermal vents might provide the energy needed for biological processes. The gravitational relationships between moons and their planets create some of the most elegant patterns in nature. Many satellite systems are locked in orbital resonances, mathematical harmonies where their periods of revolution create simple ratios. For every orbit that Europa completes around Jupiter, Io completes exactly 2, while Ganymede completes 1 for every 2 of Europa's orbits. These resonances, far from being mere cosmic coincidences, help stabilize the satellite systems over billions of years, while also providing the gravitational nudges that heat these worlds from within. As we've extended our robotic senses throughout the solar system, we've discovered that nearly every planet hosts its own family of satellites, from Mars's 2 tiny potato-shaped companions to the hundreds of small moons that shepherd the particles in Saturn's rings. Even dwarf planets like Pluto have been found to host complex satellite systems that challenge our understanding of how these relationships form and evolve. The dance between planets and moons extends far beyond our own solar system. As we've discovered thousands of exoplanets orbiting distant stars, we've begun to realize that many of these worlds likely host their own families of satellites. While we haven't yet detected these exomoons directly, their subtle gravitational influences on their parent planets may soon reveal their presence, opening an entirely new chapter in our exploration of cosmic architectures. Some of these distant moons might orbit in the habitable zones of their planetary systems, where liquid water could exist on their surfaces even if their parent planets are too hot or too cold for life. A moon orbiting a gas giant in the outer reaches of an alien solar system might receive enough tidal heating to maintain a temperate climate, creating an oasis of habitability in what would otherwise be a frozen wasteland. The story of moons is ultimately a story about relationships, about how gravitational partnerships can create conditions for complexity, beauty, and perhaps even life itself. These celestial companions remind us that in the cosmos, as in life, it's often the connections between things that create the most interesting possibilities. From the tidal pools that may have cradled the first life on Earth, to the subsurface oceans that might harbor alien ecosystems, from the ring systems that paint auroras in their planet's skies, to the orbital resonances that create stability across billions of years. Moons are the quiet architects of the planetary conditions that make worlds not just interesting, but potentially alive. As you drift towards sleep tonight, perhaps you'll dream of these distant dancers, these companions that have been waltzing through space since before the Earth was born, their patient orbits weaving the invisible threads that hold the cosmic tapestry together. Welcome back to those celestial suburbs we call home, where spiral arms sweep gracefully through the cosmic night and ancient light whispers stories of collision and creation. We've journeyed far together through the birth of galaxies and the dance of dark matter. But now our voyage takes a more intimate turn as we explore the secret lives of those quiet companions that orbit our worlds. Tonight we drift into the realm of planetary satellites, those patient dancers we call moons. You might think of them as simple rocky spheres, silent and still. But moons are far more than distant nightlights or tidal clockwork. They are sculptors of worlds, architects of atmospheres, and perhaps even midwives to life itself. From our own moon's gentle tug that stabilizes Earth's seasons to the volcanic fury of Io and the subsurface oceans of Europa, moons shape the very possibility of life across the cosmos. They are thermal engines powered by gravitational embrace, ice worlds hiding liquid seas, and atmospheric laboratories where methane rains from orange skies. Some moons are shepherds, corralling rings into elegant patterns. Others are rebels, tumbling chaotically through space after ancient collisions. A few may harbor the ingredients for life in their hidden depths, while others serve as time capsules, preserving the early history of our solar system in their cratered faces. But perhaps most remarkably, moons reveal the profound interconnectedness of celestial mechanics. They exist in gravitational resonances that ring like cosmic bells, locked in orbital dances that have persisted for billions of years. Every moon tells a story of formation through collision, capture, or co-evolution, each one a unique solution to the gravitational puzzles posed by planets and the debris of creation. As we'll discover, these satellite worlds often exist in a delicate balance between order and chaos, their surfaces constantly renewed by tidal heating, their interiors kept warm by the gravitational massage of their parent planets. Some moons are more geologically active than the worlds they orbit, their icy surfaces cracking and reforming in patterns that hint at the liquid oceans beneath. In the broader cosmic context, moons may be the rule rather than the exception. As we peer deeper into space and discover thousands of exoplanets, we're beginning to realize that many of these distant worlds likely possess their own families of satellites. The moons of Jupiter and Saturn may offer us glimpses into the diversity of worlds that populate the galaxy, each one a laboratory for understanding how gravity, chemistry, and time conspire to create environments where life might emerge. So as we settle into this gentle exploration of planetary companions, remember that every moon we encounter is both an individual world with its own personality and part of a larger gravitational symphony. They are the supporting cast that makes the planetary drama possible. The quiet partners whose influence extends far beyond their modest size. Tonight, we'll visit ice worlds and lava moons, captured asteroids and co-evolved companions, each one adding its own voice to the cosmic chorus. We'll discover how these satellite worlds don't merely orbit their planets, but actively participate in shaping climates, stabilizing rotations, and perhaps even nurturing the conditions necessary for life to flourish. The universe, it seems, has a fondness for companions, for the gentle gravitational embraces that bind worlds together in eternal dance. The universe has become a storyteller, weaving tales of gravity and time across the cosmic dark. For billions of years, moons have been the quiet dancers in this celestial narrative, spinning around their planetary partners in an ancient choreography that shapes worlds and sparks the possibility of life itself. Tonight, we drift deeper into these orbital relationships, exploring how moons don't merely orbit. They sculpt, they nurture, and they create the very conditions that make existence possible. We've already seen how moons form through cosmic collisions and gravitational capture, how they carve rings and shepherd particles, how they heat their neighbors through tidal forces and harbor hidden oceans beneath frozen shells. We've watched them dance in resonant patterns, stabilize the wobble of worlds, and create the rhythmic tides that may have cradled the first stirrings of life on Earth. But there's more to this story, something even more profound about the role these celestial companions play in the grand theater of existence. Consider for a moment the delicate balance that allows life to flourish. It's not just about being in the right place at the right time, though that certainly matters. It's about having the right conditions maintained over vast stretches of time: stable climates, protective magnetic fields, chemical cycles that can sustain complexity. And here's where moons reveal their true significance. They are the universe's way of creating persistence, of taking chaotic, violent planetary systems and turning them into stable, nurturing environments where the slow work of evolution can unfold. Take our own moon, that familiar face in the night sky that we often take for granted. Without it, Earth would be a very different world. Our planet would spin faster, with days lasting only about 6 hours instead of 24. The axis of our world would wobble wildly over time, swinging from nearly upright to dramatically tilted in cycles that would create climate chaos. Ice ages and warm periods would come and go with brutal unpredictability. The tides that helped mix the primordial oceans and may have provided the energy gradients necessary for the first chemical reactions of life would be mere whispers of their current strength. But with our moon's steady gravitational embrace, Earth has been given the gift of stability. The moon acts like a cosmic gyroscope, keeping our planet's tilt relatively constant over millions of years. This stability has allowed complex climate patterns to develop and persist, creating the reliable seasons that life has learned to depend upon. The tidal forces, while gradually slowing Earth's rotation, have also helped maintain the dynamic mixing of our oceans, driving currents that distribute heat and nutrients around the globe. This isn't unique to Earth. Throughout the solar system, we find moons playing similar roles as cosmic gardeners, tending to the conditions that make their planetary systems more hospitable to complexity and change. Jupiter's great moons, Io, Europa, Ganymede, and Callisto, each contribute to a delicate gravitational symphony that has persisted for billions of years. Their orbital resonances don't just create beautiful mathematical patterns. They regulate the flow of energy through the Jovian system, ensuring that Europa's subsurface ocean remains liquid, that Io's volcanoes continue to recycle materials, that Ganymede maintains its magnetic field. Saturn's moons perform an even more intricate dance. Enceladus, with its geysers of water ice shooting from the south polar region, is kept warm by the gravitational kneading of Saturn and its neighboring moons. This tidal heating doesn't just create spectacular plumes visible from space. It maintains a global ocean that may have persisted for hundreds of millions of years, providing a stable environment where the chemistry of life could potentially unfold in the darkness beneath the ice. Titan, wrapped in its thick atmosphere of nitrogen and methane, presents us with a world that mirrors early Earth in some ways, yet follows its own unique path. The moon's substantial atmosphere, maintained partly through interactions with Saturn's magnetosphere and the gravitational influences of neighboring moons, has created a complex weather system with methane rain, seasonal changes, and vast hydrocarbon lakes. It's a laboratory of organic chemistry, a place where the building blocks of life form naturally in an environment utterly unlike our own. But perhaps the most profound role that moons play is in expanding the definition of habitable worlds. For most of human history, we've thought of habitability in terms of surface conditions, liquid water under a breathable atmosphere warmed by a nearby star. The discovery of subsurface oceans and moons throughout the outer solar system has revolutionized this thinking. Suddenly, worlds that appear frozen and lifeless from the outside reveal themselves as potentially vibrant ecosystems hidden beneath protective shells of ice. These subsurface oceans, heated by tidal forces rather than stellar radiation, could remain stable for billions of years, even as their host stars evolve and change. They represent a new category of potentially habitable worlds, one that vastly expands the number of places in the universe where life might take hold. And they exist not despite the presence of giant planets, but because of them. Because the gravitational complexity of multi-moon systems creates the conditions necessary for long-term tidal heating. This has implications far beyond our solar system. As we discover more and more exoplanets orbiting distant stars, we're beginning to realize that many of these worlds likely have moons of their own. Some may be as large as Mars or even Earth, orbiting gas giants in the habitable zones of their stars. These exomoons could be worlds where surface and subsurface habitability combine, where tidal heating supplements stellar warming, where the gravitational dance of moon and planet creates conditions even more favorable to life than we find on solitary worlds. The story becomes even more intriguing when we consider how moons might influence the evolution of intelligence itself. The regular cycles created by lunar phases, tidal rhythms, and orbital resonances provide natural clocks that life can use to coordinate biological processes. Many species on Earth time their reproduction, migration, and feeding behaviors to lunar cycles. The predictable patterns created by moons may have provided some of the first examples of reliable environmental cues that early life forms could use to develop internal biological clocks. More speculatively, some researchers have suggested that the complex gravitational environment created by large moons might influence the evolution of intelligence in more direct ways. The tidal forces that create dynamic environments, mixing oceans, driving geological activity, creating diverse ecological niches, also create evolutionary pressures that favor adaptability and problem-solving. Worlds with active, moon-driven geology and climate systems might be more likely to produce complex, intelligent life than tidally locked or geologically dead planets. Even the simple act of having a large, visible moon in the sky might influence the development of scientific thinking. The moon's phases provided early humans with one of their first examples of predictable celestial mechanics, helping to develop concepts of cycles, mathematical relationships, and the idea that natural phenomena follow discoverable laws. The gravitational effects of the moon on tides gave our ancestors direct, observable evidence that distant objects could influence events on Earth, laying groundwork for later understanding of universal physical laws. As we look toward the future, moons continue to shape our understanding of planetary systems and their potential for harboring life. The upcoming missions to Europa, Enceladus, and Titan will search for signs of life in environments that exist because of tidal heating, because of the gravitational relationships between moons and their planetary hosts. These missions represent humanity's first serious attempts to find life in the kinds of subsurface ocean worlds that may be among the most common habitable environments in the universe. The techniques we're developing to study these distant moons are also being applied to the search for exomoons around other stars. While we haven't yet definitively detected an exomoon, several candidates have been identified, and new space-based telescopes may soon provide the sensitivity needed to confirm the existence of moon systems around distant worlds. Each detection will add another piece to our understanding of how common these orbital partnerships are and how they might influence the habitability of worlds throughout the galaxy. But perhaps the most beautiful aspect of the moon-planet relationship is how it reminds us that complexity and beauty often arise from partnership rather than isolation. The most interesting, dynamic, and potentially life-bearing worlds in our solar system are not solitary planets, but members of gravitational communities, systems where multiple bodies interact, influence each other, and create conditions that none could achieve alone. In this cosmic dance, moons are not merely passive partners following their planetary leads. They are active participants, shaping the evolution of their systems through gravitational influence, tidal heating, and orbital resonance. They turn simple planetary systems into complex, dynamic environments where change and stability coexist, where energy flows in patterns that persist for billions of years, where the conditions for life can emerge and be maintained across vast stretches of time. So as you drift towards sleep tonight, perhaps you'll think of our own moon rising silently outside your window, continuing its ancient work of stabilizing our world's climate, driving our ocean tides, and keeping our planet's axis steady. It's been performing this quiet service for over 4 billion years, long before the first life stirred in Earth's primordial seas, and it will continue long after our own species has joined the fossil record. The moon and its countless siblings throughout the universe are the universe's way of creating homes, not just places where life can exist, but places where it can persist, evolve, and perhaps eventually contemplate its own existence under the gentle light of celestial companions. The dance of moons continues around us, weaving patterns of gravitational influence that stretch far beyond our own cosmic neighborhood. As we've explored the intricate relationships between planets and their satellites, we've seen how these celestial partnerships create the conditions for life, drive geological activity, and maintain the delicate balance necessary for habitability. But the story of moons extends beyond our solar system, reaching into the vast expanse of space where thousands of exoplanets orbit distant stars. When astronomers first began discovering exoplanets in the 1990s, they found worlds unlike anything in our solar system. Hot Jupiters orbiting closer to their stars than Mercury orbits our sun, super-Earths with no analog in our cosmic backyard, and systems where planets dance in resonant chains that would make our own solar system seem chaotic by comparison. Yet as we've learned more about these distant worlds, we've come to appreciate that the principles governing planetary satellites likely apply throughout the galaxy. The search for exomoons, as they're called, represents one of the most challenging frontiers in astronomy. While we can detect the subtle dimming of starlight as a planet passes in front of its host star, finding a moon requires detecting an even smaller signal, a whisper within a whisper. The moon's gravitational influence on its planet creates tiny wobbles in the planet's orbit, shifts in the timing of transits, and minute changes in the duration of these celestial eclipses. These signatures are so subtle that they push our current technology to its limits. Despite these challenges, astronomers have identified several promising candidates for exomoons. Some may be as large as Neptune, orbiting gas giant planets in the habitable zones of their stars. These moon systems could harbor conditions suitable for life, with the satellite receiving energy not only from its distant star, but also from tidal heating generated by its gravitational dance with the host planet. Imagine a world where auroras paint the sky in colors we've never seen, powered by the magnetic field interactions between planet and moon. while subsurface oceans remain liquid thanks to the constant kneading of tidal forces. The potential for life on exomoons opens up extraordinary possibilities for habitability throughout the galaxy. While a planet might orbit too far from its star to maintain liquid water on its surface, a large moon of that planet could be kept warm through tidal heating, creating a habitable world in what would otherwise be a frozen wasteland. This expands the traditional concept of the habitable zone, suggesting that life might thrive in places we never thought to look. Consider the implications for planetary systems with multiple large moons. Each satellite would create its own pattern of tidal forces, gravitational resonances, and orbital dynamics. The interplay between these moons could create complex cycles of heating and cooling, seasonal variations unlike anything we experience on Earth, and evolutionary pressures that might drive life in directions we can barely imagine. On one moon, life might adapt to extreme tidal ranges that expose vast areas of ocean floor twice each day. On another, organisms might evolve to take advantage of the regular eclipses created by neighboring moons, developing photosynthetic processes that operate in the unique spectral conditions of filtered starlight. The gravitational architecture of exomoon systems could also influence the long-term stability of planetary climates. Just as our moon helps stabilize Earth's axial tilt, preventing dramatic climate swings, exomoons might serve similar roles for their host planets. A system with multiple large moons could create an even more stable environment, with the satellites working together to dampen any perturbations that might otherwise lead to chaotic climate variations. This stabilizing influence could be crucial for the development of complex life, providing the billions of years of relatively stable conditions necessary for evolution to produce sophisticated organisms. The formation mechanisms for exomoons likely mirror those we see in our own solar system, but with variations that reflect the diversity of planetary systems throughout the galaxy. In systems where giant planets migrated inward toward their stars, any primordial moons might have been stripped away, only to be replaced by captured asteroids or formed through giant impacts. Some exomoons might have formed from the debris of planetary collisions, creating satellite systems with compositions dramatically different from their host planets. The study of exomoons also sheds light on the role of moons in planetary evolution. In our solar system, we've seen how the moon's formation likely contributed to Earth's iron core formation and may have influenced the development of plate tectonics. Similar processes might operate in exoplanetary systems, with large moon-forming impacts shaping not only the satellites, but also the internal structure and geological evolution of the planets themselves. As our detection methods improve and future space telescopes come online, we expect to discover not just the first confirmed exomoons, but entire moon systems around distant planets. These discoveries will reveal whether the intricate gravitational relationships we see in our own solar system are common throughout the galaxy or represent something unique to our cosmic neighborhood. Each new exomoon system will provide another data point in our understanding of how planets and satellites co-evolve, how they influence each other's habitability, and how they contribute to the complex dance of forces that shapes planetary systems over billions of years. The dance of moons, it turns out, is not just a local phenomenon, but a cosmic ballet performed on stages throughout the galaxy. Every distant star likely hosts its own choreography of planets and satellites, each system telling its own story of gravitational partnership, tidal evolution, and the endless creativity of celestial mechanics. As we continue to explore these distant worlds, we're not just expanding our catalog of known objects in the universe, we're deepening our understanding of the fundamental processes that make worlds habitable and life possible. The cosmos has been calling for billions of years, And finally, we're beginning to answer. Over the past 4 centuries, we've discovered that our universe is not just vast, it's alive with worlds beyond imagination. Planets dance around distant stars in cosmic choreographies we're only now learning to read. And tonight, we're going to explore one of the most elegant and mysterious partnerships in all of space: the secret lives of planetary satellites. Now, you might wonder why moons matter. After all, they're just rocks orbiting other rocks, aren't they? But as we'll discover together, moons are far more than silent companions. They're architects of stability, creators of tides, sculptors of climate, and perhaps most remarkably, they may be the most likely places in our universe to harbor life. We've journeyed through the formation of these celestial dancers, watched them emerge from cosmic collisions and gravitational captures. We've seen how they stabilize their planets, create the very rhythms that allowed life to flourish on Earth, and how they hide vast oceans beneath their icy shells. We've explored the intricate gravitational resonances that keep them locked in perfect mathematical harmony, and we've ventured beyond our solar system to imagine the moons that might orbit distant exoplanets. But now, as we approach the end of our cosmic voyage, we must ask ourselves, what does it all mean? What can these dancing moons teach us about our place in the universe? And what might they reveal about the future of life itself? The answer lies in something profound yet simple: connection. Every moon we've encountered tonight tells a story of partnership, of 2 or more worlds bound together by invisible threads of gravity, spinning their way through space in an eternal embrace. These aren't isolated objects floating randomly through the void. They're members of families, communities of worlds that shape and support each other across billions of years. Consider Europa, that enigmatic moon of Jupiter we've visited several times tonight. Beneath its cracked and shifting ice lies an ocean that may have existed for longer than complex life has existed on Earth. The tidal forces from Jupiter, those same forces that would tear apart a smaller moon, instead become Europa's lifeblood, generating the heat that keeps its ocean liquid and drives the chemistry that might, even now, be nurturing life in its dark depths. This is the paradox of moons. They exist in a delicate balance between destruction and creation. Too close to their planet, and they're torn apart by tidal forces. Too far away, and they drift into the cold emptiness of space. But in that narrow zone between, in that sweet spot of gravitational harmony, they become something extraordinary. Worlds where the impossible becomes possible. The same story plays out across our solar system and likely throughout the galaxy. Enceladus spews geysers of water into space, powered by the gravitational massage of Saturn and its neighboring moons. Titan, with its thick atmosphere and methane lakes, shows us what Earth might have looked like in its youth, while Io demonstrates the raw volcanic power that tidal heating can unleash. Each of these worlds exists because of its relationship with others. They are not self-made. They are community-made, shaped by the invisible hands of gravity reaching across hundreds of thousands of kilometers of space. This interconnectedness extends beyond individual moon systems to influence entire planetary environments. Our own moon doesn't just light up our nights and drive our tides. It stabilizes our planet's axial tilt, preventing the wild climate swings that would make complex life nearly impossible. Without our moon, Earth might look more like Mars, a world where the atmosphere has been stripped away and the climate fluctuates wildly over geological time. The moon also gave us time itself, in a sense. The regular rhythm of lunar phases provided our ancestors with their first calendar, their first way of measuring the passage of weeks and months. The tides it creates may have provided the very evolutionary pressure that drove life from the oceans onto land. In countless ways, we are children of the moon as much as we are children of the sun. As we've ventured beyond our solar system in our imagination, we've discovered that this dance of moons and planets likely plays out around countless other stars. The exomoons we cannot yet directly observe may be among the most common habitable worlds in the galaxy. While we search for Earth-like planets in the habitable zones of their stars, we may be overlooking an even more abundant class of worlds. The Europa-like moons that could harbor life in oceans, heated not by starlight, but by the gentle friction of gravitational love. These hidden oceans expand the habitable zone of every planetary system far beyond the narrow band where liquid water can exist on a planet's surface. A moon like Europa could remain habitable even if its host planet orbited far from its star, in the cold outer reaches of the system. This means that every gas giant, every system with large planets, potentially hosts multiple worlds where life might flourish in hidden seas. The implications are staggering. If moons are indeed more numerous than planets, and if they can remain habitable under a wider range of conditions, then the universe may be far more alive than we ever dared imagine. Every star system might host not just one or two potentially habitable worlds, but dozens of them, hidden beneath the ice of countless moons. But perhaps the most profound lesson these celestial dancers teach us is about the nature of stability itself. In a universe governed by entropy, where everything tends toward disorder and decay, gravitational systems like moon-planet pairs represent islands of order and harmony. They show us that even in the vast emptiness of space, structure can emerge, relationships can form, and beauty can persist for billions of years. The resonances we've explored, the mathematical music of orbiting worlds, reveal a universe that operates not on chaos, but on deep mathematical principles. When we see the moons of Jupiter locked in their intricate dance, with Io completing 4 orbits for every 2 of Europa and every 1 of Ganymede, we're witnessing the universe composing a symphony in the language of orbital mechanics. These resonances aren't random accidents. They're attractors, stable configurations that systems naturally evolve toward. They represent the universe's tendency to find harmony even in the midst of apparent chaos. In a cosmos where collisions and catastrophes are common, these gravitational partnerships show us that cooperation and mutual support are just as fundamental as competition and destruction. As we look toward the future, moons will likely play a crucial role in humanity's expansion into space. The moon, our nearest celestial neighbor, may become our first permanent foothold beyond Earth. Its low gravity and lack of atmosphere make it an ideal launching pad for missions deeper into the solar system. The ice at its poles could provide water, oxygen, and hydrogen fuel for future explorers. Beyond our moon, the moons of the outer planets beckon as some of the most intriguing destinations for future missions. Europa and Enceladus, with their subsurface oceans, represent our best chance of finding life beyond Earth within our own solar system. Titan, with its thick atmosphere and complex chemistry, offers a laboratory for understanding prebiotic chemistry and the conditions that might have led to life's emergence. But perhaps most importantly, studying moons teaches us about resilience and adaptation. These worlds show us that life doesn't require perfect conditions. It requires stable, long-term conditions. The moons that harbor subsurface oceans have maintained liquid water for billions of years, far longer than the surface oceans of many planets might remain stable. This is a lesson worth remembering as we face the challenges of climate change and environmental uncertainty on our own world. The story of moons reminds us that sustainability isn't about finding the perfect moment. It's about maintaining the delicate balances that allow complex systems to persist over vast stretches of time. As we drift toward the end of our journey tonight, I want you to imagine stepping outside and looking up at the moon, our moon, that bright companion that has watched over every human story ever told. Remember that you're not just looking at a dead rock in space. You're looking at a partner, a dance partner that has been spinning with Earth for over 4 billion years. That moon helped create the very conditions that allowed you to exist. It stirred the primordial oceans, stabilized our planet's climate, and gave our ancestors the rhythms by which they first learned to measure time. Every breath you take, every heartbeat, happens within the gravitational embrace of that ancient partnership. And beyond our moon, throughout our solar system and across the galaxy, countless other worlds are engaged in their own cosmic dances. Moons we may never visit are sculpting the destinies of planets we'll never see, creating the conditions for stories we'll never know. In the hidden oceans of distant moons, life may be stirring, thinking its first thoughts, taking its first tentative steps toward complexity and consciousness. The universe, we've learned, is not a lonely place. It's a place of partnerships, of gravitational bonds that tie worlds together across the vast emptiness of space. These bonds are not just physical, they're creative, generative forces that sculpt worlds, drive evolution, and create the very possibility of life itself. So the next time you see the moon rising over the horizon, or catch Jupiter and its dancing moons through a telescope, remember that you're witnessing one of the universe's most beautiful and fundamental phenomena, the ancient art of celestial partnership. You're seeing gravity transformed from a simple attractive force into something far more profound, a creative principle that builds worlds, nurtures life, and writes the most beautiful stories in the language of orbital mechanics. The moons are dancing still, as they have for billions of years, as they will for billions more. And in their dance, they carry the secret of how the universe creates beauty, stability, and perhaps even consciousness itself from the simple attraction of mass to mass, world to world, across the infinite expanse of space and time. The dance continues, and we are part of it. We are children of dancing worlds, inheritors of a cosmic choreography that began before the Earth was born and will continue long after our sun has faded to a whisper. In that dance, in that eternal partnership between worlds, we find not just the secret lives of planetary satellites, but the secret of life itself. Sleep well, fellow travelers. As our cosmic journey draws to a close, we find ourselves at the threshold of the greatest mystery of all, the question that has haunted humanity since we first gazed upward at the star-swept darkness above. After wandering through billions of years of galactic evolution, after witnessing the birth of stars and the slow dance of spiral arms, after peering into the depths of space and time itself, we arrive at the most profound question our species has ever asked. Are we alone? It's a question that feels both intimate and infinite, personal and cosmic. Here we are, perched on a small blue world orbiting an ordinary yellow star in the outer reaches of a spiral galaxy that is itself just one of hundreds of billions scattered across the observable universe. Earth, for all its beauty and complexity, occupies less space in the cosmos than a grain of sand on an endless beach. And yet, as far as we know, it is the only place where life has taken hold, where consciousness has emerged, where someone can ask the question at all. The search for life beyond Earth has become one of the great scientific quests of our time, a modern expedition into the unknown that combines cutting-edge technology with humanity's oldest dreams. We call it astrobiology, the study of life in the universe, and it encompasses everything from hunting for microbes in Martian soil to listening for radio signals from distant civilizations. It's a field that didn't even exist a few decades ago, born from our growing understanding of just how vast and varied the cosmos truly is. The story begins, perhaps surprisingly, not with telescopes pointed at distant stars, but with discoveries much closer to home. For most of human history, we assumed that life required very specific, very delicate conditions to survive. Liquid water at just the right temperature, a protective atmosphere, a stable climate. Earth seemed like a cosmic miracle, a perfect storm of favorable circumstances that allowed biology to flourish. Life, we thought, was fragile, rare, and probably confined to places very much like our own world. But then we started looking more carefully at life on Earth itself, and what we found was astonishing. In the crushing depths of the ocean, where sunlight never penetrates and pressure would flatten a human instantly, we discovered thriving ecosystems clustered around hydrothermal vents, underwater geysers that spew superheated, chemically rich water into the abyss. The creatures living there don't depend on photosynthesis, the process that powers most life on Earth's surface. Instead, they derive energy from chemicals, thriving in conditions that would have seemed utterly hostile just decades ago. We found life in the most acidic hot springs, in the saltiest lakes, in the coldest Antarctic valleys. We discovered bacteria living miles underground, feeding on radioactive decay. We found microorganisms that can survive the vacuum of space, that can endure radiation levels that would be lethal to any complex organism, that can remain dormant for millions of years and then spring back to life when conditions improve. These extremophiles, as they're called, shattered our assumptions about where life could exist. If biology could thrive in such hostile environments on Earth, then perhaps the universe held far more potential homes for life than we had ever imagined. This revelation transformed our approach to astrobiology. Instead of looking only for Earth-like worlds with Earth-like conditions, scientists began to consider a much broader range of possibilities. What about the subsurface oceans of Jupiter's moon Europa, hidden beneath miles of ice? What about Saturn's moon Enceladus, which shoots geysers of water vapor into space from its southern pole? What about the methane lakes of Titan, or the ancient riverbeds of Mars? Suddenly, our own solar system seemed full of places where life might exist, even if that life looked nothing like what we're familiar with. The search for life beyond Earth takes many forms, each with its own hopes and challenges. On Mars, robotic rovers crawl across the rusty landscape, drilling into rocks and analyzing soil samples, looking for chemical signatures that might indicate past or present biological activity. Mars was once a very different world, with flowing rivers and possibly even oceans. If life ever emerged there, traces of it might still be preserved in the planet's geological record, waiting to be discovered by our mechanical explorers. Beyond our solar system, the hunt becomes even more ambitious. The Kepler Space Telescope and its successors have revolutionized our understanding of planetary systems, revealing that planets are not rare cosmic accidents, but common features of the galaxy. We now know of thousands of exoplanets, worlds orbiting other stars, and many of them fall within what astronomers call the habitable zone, the region around a star where liquid water could exist on a planet's surface. Some of these distant worlds are tantalizing. Kepler 452b sometimes called Earth's cousin, orbits a star similar to our Sun at a distance that could allow for liquid water. Proxima Centauri b, the closest known exoplanet to Earth, sits in the habitable zone of our nearest stellar neighbor. TRAPPIST-1, a small red star just 40 light-years away, hosts 7 Earth-sized planets, 3 of which might be capable of supporting liquid water. Each discovery adds another chapter to the growing catalog of worlds that might, just might, harbor life. But finding potentially habitable planets is only the first step. The real challenge lies in determining whether any of them actually do host life, and that requires techniques at the very edge of our technological capabilities. Astronomers are developing methods to analyze the atmospheres of distant worlds, looking for biosignatures, chemical fingerprints that might indicate biological processes. Oxygen, for instance, is highly reactive and would quickly disappear from a planet's atmosphere unless something was continuously producing it. On Earth, that something is photosynthesis. If we could detect oxygen in the atmosphere of a distant planet, especially in combination with water vapor and other gases, it might be evidence of life. The James Webb Space Telescope, humanity's most powerful space observatory, has already begun this delicate work. It can analyze the light from distant stars as it filters through the atmospheres of their planets, breaking that light into its component wavelengths to reveal the chemical composition of alien air. It's an extraordinary feat of technology and scientific ingenuity, reading the atmospheric composition of worlds so distant that their light takes years or decades to reach us. But perhaps the most ambitious, and certainly the most romantic aspect of the search for extraterrestrial life is the hunt for intelligence, for civilizations that might be trying to communicate across the vast distances of space. SETI, the search for extraterrestrial intelligence, represents humanity's attempt to listen for signals from other technological civilizations, to detect the electromagnetic whispers of distant worlds that have developed their own science, their own technology, their own questions about the universe. The concept is elegantly simple. If other civilizations exist and have developed radio technology, they might be broadcasting signals into space, either deliberately or as a byproduct of their activities. Radio waves can travel across interstellar distances with relatively little interference, carrying information from one star system to another. SETI researchers use sophisticated radio telescopes to scan the sky, listening for patterns that might indicate artificial origin, signals too structured, too regular, or too purposeful to be natural phenomena. The search has been going on for decades, and so far we have heard only silence. But that silence is not necessarily meaningful. Space is vast beyond imagination, and radio signals weaken with distance. A civilization would need to be broadcasting with tremendous power for us to detect their signals across interstellar distances, or we would need to be extraordinarily lucky to catch a brief transmission aimed in our direction. The absence of detected signals doesn't mean there's no one out there. It might simply mean we haven't been listening long enough, or in the right direction, or at the right frequency. There's also the sobering possibility that civilizations might not last long enough to make contact. 8 billion years old, but technological civilization on Earth has existed for only a few centuries. If most intelligent species follow a similar pattern, developing technology quickly, but then facing existential challenges like climate change, nuclear war, or resource depletion, then civilizations might be like flickering candles in the cosmic darkness, burning brightly but briefly, rarely overlapping in time despite the vastness of space. Given the age of the universe, the vast number of stars and planets, and the apparent ease with which life emerged on Earth, it seems reasonable to expect that intelligent civilizations should be common. Yet we see no evidence of them. No radio signals, no artifacts, no obvious signs of large-scale engineering projects that a sufficiently advanced civilization might undertake. Various solutions to the Fermi paradox have been proposed. Perhaps life is much rarer than we think, requiring such an unlikely confluence of circumstances that Earth is essentially unique. Perhaps intelligence is the rare thing. Life might be common, but complex. Technological life might be extraordinarily unlikely. Perhaps civilizations do exist, but are deliberately staying quiet, following some kind of cosmic etiquette that prevents them from revealing themselves to younger species like ourselves. Or perhaps they exist, but are so advanced that their activities are simply beyond our ability to recognize or understand. Each possibility carries its own implications for humanity's place in the cosmos. If we are truly alone, then we bear an extraordinary responsibility as possibly the only conscious observers in an otherwise unconscious universe. If we are rare but not unique, then we are part of a small but precious community of thinking beings scattered across the galaxy. If we are common but simply haven't made contact yet, then the future might hold the most profound discovery in human history: the realization that we are not alone. Recent developments have added new dimensions to the search for extraterrestrial life. The discovery of organic molecules on Mars, the detection of phosphine in the atmosphere of Venus, a gas that on Earth is primarily produced by living organisms, and the identification of potentially habitable exoplanets have all contributed to a growing sense that life might be more common than we once thought. We're also developing new tools and techniques, from improved methods of analyzing planetary atmospheres to more sophisticated approaches to SETI that look beyond radio signals to include optical flashes, infrared signatures, and even the possibility of detecting large-scale engineering projects around distant stars. The question of extraterrestrial life also forces us to confront deeper philosophical questions about the nature of life itself. How do we define life? Is it simply a matter of chemistry? Self-replicating molecules that can evolve and adapt? Or is there something more fundamental? Something that distinguishes living systems from non-living ones? As we search for life beyond Earth, we're also refining our understanding of what life actually is, what forms it might take, and how we might recognize it when we find it. These questions become even more complex when we consider the possibility of artificial intelligence. If we do encounter evidence of extraterrestrial intelligence, will it be biological, like ourselves? Or might it be artificial, the product of a biological civilization that has transcended its original form? Some researchers suggest that any civilization old enough and advanced enough to communicate across interstellar distances might have long since merged with or been replaced by artificial intelligence. The signals we're looking for might not come from beings of flesh and blood, but from vast computational systems that represent the ultimate evolution of intelligence in the universe. As we stand on the threshold of potentially answering one of humanity's most profound questions, it's worth considering what such a discovery would mean. The detection of even simple microbial life beyond Earth would represent a fundamental shift in our understanding of our place in the cosmos. It would suggest that life is not a unique accident, but a natural consequence of the right conditions, that the universe might be teeming with biology in forms we can barely imagine. The discovery of intelligent life would be even more transformative. It would end humanity's cosmic loneliness, confirming that consciousness and intelligence are not singular phenomena, but features of the universe as fundamental as stars and galaxies. It would raise profound questions about communication, cooperation, and the future of intelligence in the cosmos. It would force us to see ourselves not as the pinnacle of evolution, but as one branch on a vast tree of consciousness that spans the galaxy. But even if we never find definitive evidence of life beyond Earth, the search itself has value. It drives technological innovation, inspires scientific discovery, and forces us to think carefully about what makes life special and precious. It connects us to the cosmos in a fundamental way, reminding us that we are not separate from the universe, but part of it. Made of the same atoms forged in the hearts of ancient stars, governed by the same physical laws that shape galaxies and guide the dance of planets around distant suns. The search for extraterrestrial life is ultimately a search for context, an attempt to understand whether our existence is a cosmic miracle or part of a larger community of conscious beings. It's a question that touches on science and philosophy, on our deepest fears and our greatest hopes. Whether we find life beyond Earth or confirm our cosmic solitude, the answer will profoundly shape how we see ourselves and our responsibilities to each other and to the universe that gave birth to us. So as you drift toward sleep tonight, carried by the gentle rhythm of your breathing and the quiet beating of your heart, remember that you are part of this grand cosmic story. Every atom in your body was forged in the nuclear furnace of a star. Every breath connects you to the thin atmosphere of a small planet orbiting an ordinary star in a galaxy filled with hundreds of billions of other suns. You are made of star stuff, shaped by the same forces that carved spiral arms and lit the first lights in the cosmic darkness. Whether you are alone in the universe or part of a vast community of conscious beings, you are here, now, aware and wondering. You carry within you the capacity to ask questions that span billions of years and billions of light years, to seek answers that might reshape our understanding of existence itself. In a cosmos vast beyond imagination, in a universe that might be filled with life or might be profoundly empty, you are a rare and precious thing, a fragment of the universe that has become aware of itself, a brief candle flame of consciousness flickering in the cosmic night. And perhaps, somewhere out there among the stars, another being on another world is looking up at their own night sky, asking the same questions, wondering if they too are alone. Perhaps they too are made of star stuff, shaped by gravity and time, warmed by the light of their own sun. Perhaps they too are drifting towards sleep, carried by their own version of breath and heartbeat, dreaming their own dreams of distant worlds and cosmic connection. The universe may be vast and ancient and mysterious, but it has given rise to you, to consciousness, to the capacity for wonder and the ability to dream. Whether you are the only such being in the cosmos or one of countless billions, you are a miracle. A beautiful, temporary arrangement of atoms that can contemplate infinity, can ask questions about its own existence, can reach across the darkness toward distant stars and wonder, with equal parts hope and humility, whether anyone is reaching back. Sleep well, fellow traveler in the cosmic dark. You are home among the stars, part of the greatest story ever told, a living, breathing, dreaming chapter in the universe's long journey toward understanding itself. The search for life beyond Earth continues, carried forward by our curiosity, our technology, and our profound need to know whether we dance alone or in company among the galaxies. And whatever the answer, you are here. You are conscious. You are wondering, and that itself is perhaps the most extraordinary fact in all the cosmos.